And yes, and then after this background, I will tell you about the main result of our talk. At least from my point of view, it's main result that the Bousfield-Kan completion can be described as a particular case of this general notion of codensity monad, but in the setting of infinity category theory, not in the classical setting. And then up to this point, I will try to not assume that you know something about infinity categories, but in the end, I will tell some more technical details where I will assume that you know something about infinity categories. Okay, but first, let me tell you about monads. And I will start from introducing the notion of strict monoidal category. Strict monoidal category is just category equipped with some factor of tensor product, which is strictly associative without any isomorphisms, just strict equation, and strictly unital. Usually, maybe people consider monoidal categories, which are more general, where associativity is only up to isomorphism, but we don't need them. Because we don't need them because the main example for us will be the category of end factors of some category. This category, objects of this category are functors from C to C, and morphisms are natural transformation, and composition of functors from C to C defines the structure of strict monoidal category. It is strictly associative, so we can speak about only strict monoidal categories. And another, this is the first important example, and the functors of some category. And the second important example is just one particular category called augmented simplex category, denoted by delta plus. Ordinary simplex category delta is the standard category in simplicial homotopy theory, in the definition of simplicial set, but here we slightly extended, assuming that the objects are not only non-empty finite ordinals, but we also include the empty finite ordinal, which is just natural number 0. Here I use set theoretical notation for natural numbers. I assume that natural number n is the set consisting of all previous natural numbers, and in particular 0 is the empty set. So we include the empty set to our category, and morphisms are order-preserving maps. On this category, basically objects of this category are natural numbers, and you can add, you have operation of addition or summation of natural numbers. No. Including non-injective maps, like in the definition of simplicial set. We have phase maps and degeneracy maps as well. Okay, there is operation of addition or summation, and you can think about it as disjoint union. But here you have passets, and you need to define the order, and this join of two passets is disjoint union such with the order defined so that elements of the first passet are all smaller than elements of the second passet. This we call join of passets, and this defines some operation which is on object as just addition, and it can be extended to a functor, and it gives you a structure of strict monoidal category on this delta plus. Where the unit is just empty set. We have to include the empty set because we need unit here. Okay, these are two main examples, and the functors and augmented simplex category. Okay, now I want to define notion of monoid in a strict monoidal category. Ordinary monoid is a set together with product operation and unit element. Here the definition is similar, but instead of product we have this tensor product in our category E, and so a monoid in the strict monoidal category E is an object together with a multiplication map and together with unit map, satisfying some standard axioms written in terms, expressed in terms of commutative diagrams. usual associativity axiom and unit axiom. And okay, we have two main examples of strict monoidal categories. One of them is delta plus. What monoids do we have in this augmented simplex category? We have one very special monoid in this category, namely the one element, one object set, one element set, I mean, single point. It is called walking monoid. It is a very important example of monoid in a strict monoidal category. It is defined by the unique map from two element set to one element set, and the unique map from the empty set to one element set. And it is called walking monoid because it satisfies the following universal property. The universal property says that for any monoid M in a strict monoidal category E, there exists a unique strict monoidal functor from delta plus to E, sending this special walking monoid 1 to the monoid M. So using this correspondence, using this universal property, you can identify monoids in E and functors from delta plus to E that respect strict monoidal structure of these categories. And this is very convenient thing for generalizations. Later I will define the monoid in infinity category, which will be just a functor from delta plus to infinity category satisfying some properties. Okay, what is a monad? Yes, as I already said, we have two examples of strict monoidal categories. One is delta plus, another is this category of n functors. And a monoid in the category of n functors is called monad. So if we unpack this definition of monoid, we obtain that this is that a monad is a functor from category C to itself, equipped with a natural transformation from M square, where M square means composition of M with itself, to M, and natural transformation from the identity functor to M, satisfying these two associativity and unit axioms expressed in the form of commutative diagrams. Okay, this looks like very abstract definition, but let me give you some simple examples of monads. For example, any ring or commutative ring, but for the moment it doesn't matter. You can take any ring R, but later we will always assume that R is commutative, so let it be commutative. For any ring R, and we denote, and any set X, we denote by R times X, the free module generated, free R module generated by X. And this gives you a functor from the category of sets to itself. Like we forget the structure of module here, sending X to the free module generated by X. And this functor has a natural structure of a monad, namely the unit of this monad is just the inclusion of the basis to the free module, the standard inclusion, and the multiplication map is a map from this free module generated by all elements of the free module generated by X to the free module generated by X, which can be defined on the basis. This is our homomorphism, which can be defined on the basis as the identity map. So these two guys define a structure of a monad here. Okay, now I will give you slightly more sophisticated version of this example. Actually, here it is not very important that we start from a ring, or you can do the same for any algebraic structure. You can replace free modules by free groups or free whatever, any algebraic structure, and this will give you some monad on the category of sets. And now I want to give you a slightly more sophisticated version of this, where we replace modulus by affine R-affine subsets, R-affine spaces. What do I mean by R-affine space? By affine space, I mean a subset of R module, which is closed with respect to affine linear combinations. What is affine linear combination? Affine linear combination is a linear combination such that the sum of coefficients is equal to 1. So yes, a affine subspace of a module is not necessarily a submodule, but it should be closed with respect to affine combinations. And we consider the affine subset, which is generated by X. So it is just the set of all affine linear combinations of elements of the basis. And this subset, it is natural subset, natural by X, so it is a subfunctor. And the structure of monad on this guy induces structure of monad of this guy. So we obtain a functor from the set from the category of sets to itself with a natural structure of a monad. And this monad will be later used to construct the Bousfield-Kan completion. Okay, so I gave you two examples of monads, and you can find actually, okay, later I will give you more. Another topic is notion of codensity monad. And here, first I need to start with a monad associated with adjunction. Actually, all of the previous examples of monads that I give are particular examples of this more general stuff. If you have a pair of adjoint functors, if you have two categories C and D and pair of adjoint functors F and G, then you can consider the composition from C to C, composition this GF. And this composition has a natural structure of a monad. Any pair of adjoint functors comes together with a unit and co-unit of adjunction, and you can use them to define this additional structure. Namely, the unit of adjunction will be the unit of this monad, and in order to define multiplication map, you have to use the co-unit. Co-unit of adjunction is such a natural transformation, and using this epsilon, you can construct some map from the square of this composition to itself. This will define the structure of monad. And actually, all monads can be obtained in this way. For any monad, you can construct some pair of adjoint functors such that this monad is obtained from this pair of adjoint functors in this way. Note that here I denote this monad by Tg, because actually it depends only on G after isomorphism. If you have a functor G which has left adjoint, then this left adjoint is uniquely defined up to isomorphism, and all the data is uniquely defined up to isomorphism. So this monad up to isomorphism depends only on G. And the point is that you can generalize the construction of this monad associated with adjunction to the case when G is not necessarily right adjoint. Now we assume that G is just any functor, which doesn't have any adjoint functor. And we say that and we can define Tg as the right Kan extension of the functor G along itself. It turns out that this is a generalization of the previous case. If this monad G, if this functor G has left adjoint, then this Tg will be the composition of these two functors, of the functor G with its left adjoint. But this functor G exists in a much more general case. It not always exists, but for example, if C has all small limits and D is a small category, this exists. So, and it exists much more often than just when G has a left adjoint. I will give you some more examples later. And this functor is called the codensity monad. But actually, I don't need such a high generality. Let me now restrict the generality and assume later that D is just a subcategory of C. And this G is an inclusion functor. And not just subcategory, but full subcategory. So now we assume that D is a full subcategory of C, and G is the inclusion of D into C. And in this case, we denote this codensity monad by DC. And in this case, the definition is much more clear because In the case of full subcategory, right-Kan extension gives you a commutative triangle, or commutative up to isomorphism. And you can say that the codensity monad of a full subcategory D inside of C is the universal functors such that from C to C such that this diagram is commutative. Universal terminal, it is a terminal object in the category of all functors from C to C such that this triangle is commutative. Maybe there are many other functors which give you this commutative triangle, but this one is a universal one. Another one is the identity functor. Of course, if you take the identity functor from C to C, this diagram will be commutative. So since this TD is terminal, you can say, okay, I have the natural transformation from the identity functor to TD. And another example, if TD satisfies this property, then its square also satisfies this property. It also gives you a commutative triangle here. So you also have a natural transformation from the square to T itself. And these two maps together give you a structure of a monad. So initially this TD is defined as a functor, but using the universal property, we can also equip this functor with a structure of a monad. And this is called the codensity monad of full subcategory. Okay, some examples. Maybe the most elementary example which I can give is the double dual of a vector space. Assume that K is a field, and for any vector space V over this field, we denote by this symbol the dual vector space, just home from the vector space to the field. And it is contravariant functor, but if we compose it with itself, we obtain a covariant functor from the category of vector spaces to itself. And we know that the double dual of a finite dimensional vector space is isomorphic to the original vector space, but it is not true for all vector spaces. And this gives you, and it turns out that this is terminal functor among all functors which give you a commutative triangle like this. So it is a codensity monad of the subcategory of finite dimensional vector spaces inside of the category of all vector spaces. Another similar example is finite completion of a group. If you have a group G, you can take the limit of all its finite quotients by the diagram of all normal subgroups such that the quotient is finite. And this will be profinite completion. And similarly, you can say that this one is the codensity monad of the subcategory of finite groups inside of the category of all groups. It is easy to see that profinite completion of a finite group is the finite group itself, but in general it's not true. And note that it is not this functor. Moreover, that this functor is not idempotent functor for non-finitely generated groups. So this gives you, this is quite tricky functor, but it is identical on finite groups, and this is codensity monad of the subcategory of finite groups in the category of all groups. And one more similar example is the ultrafilter monad. For those of you who remember the notion of ultrafilter, I can say that you can consider the functor from the category of sets to the category to itself, sending each set to the set of ultrafilters on it, and it preserves finite sets. And this will be the codensity monad of the category of finite sets. And actually, there is a nice paper about it. Good introductory paper to the notion of codensity monad called Codensity and Ultrafilter Monad by Tom Leinster. Yes. It is related to Stone-Check compactification, but the unit map is obvious without it. Yes. for any point of a set, there is a principal ultrafilter, and this principal, this map sending every point to the principal ultrafilter is the unit map. But on the other hand, it's true that you can treat the set of ultrafilters as the Stone-Čech compactification of the set with discrete topology. It is related, but you don't have to. And actually, I wanted to tell you about the Stone-Čech compactification because of this relation. And Stone-Čech compactification is, of course, a codensity monad of the subcategory of compact spaces inside of the category of full topological spaces. That's right. In part, and on discrete sets, it coincides with the previous guy. And completion of a metric space is a codensity monad of the subcategory of complete metric spaces. Or if you prefer, you can use uniform spaces. Completion of a uniform space is also codensity monad of the subcategory of complete uniform spaces in the category of all uniform spaces. Abelianization of a group is, of course, codensity monad of the subcategory of abelian groups inside of the category of all groups. But in some sense, these examples are not very interesting because they are idempotent. They can be reduced to the notion of localization. There is also a notion of localization factor, which is a particular case of codensity monads. I will tell you about it on the next slide, I think. Okay, one more example from commutative algebra. Here I just want to show you that codensity monads are everywhere in all mathematics. You can find some codensity monads and one more codensity monad from commutative algebra. If you have a commutative ring R, if you consider the category of commutative rings and a subcategory of fields, the associated codensity monad exists, and it sends a commutative ring R to the product indexed by all prime ideals of R, product of fraction fields of the quotients. And this is not idempotent. These three are idempotent, but the last one is not idempotent. So it is more interesting example in some sense for us. Okay. Yes, I already mentioned that sometimes codensity monads are idempotent and sometimes are not. And when they are idempotent, they are called localizations. If the subcategory of the category C is reflective, what does it mean? Reflective subcategory is category such that the inclusion functor has left adjoint. A left adjoint, yes. And then you can take the composition of this left adjoint functor from C to Z together with the inclusion. And this composition is called the localization functor associated with the reflective category, subcategory D. And in this case, codensity monad coincides with the localization functor. And in this case, it is, and this happens if and only if it is idempotent. So you can, if you are familiar with localizations, you can treat codensity monads as generalization of localization factors to arbitrary, not necessarily reflective subcategories. Codensity monads of full subcategories here, I mean. Okay, another point of view on codensity monads is that it satisfies some additional universal property. If we have a full subcategory D inside of some category C, and we have some monad on C, we say that this monad is D preserving if this unit map, the D component of the unit map is an isomorphism for all objects D of D. In this case, we say, okay, M preserves D. This is because this is an isomorphism. And it turns out that this codensity monad, as a monad, not just a functor, has some universal property. It is the terminal object in the category of all D preserving monads. So yes, there's another point of view on all these guys. And as far as I understand, this property is specific for the codensity monads of full subcategories. It doesn't work for general codensity monads of functors. Okay, this was background about category theory, and now some background about algebraic topology. And first, I want to remind you such classical notions as rationalization of one connected space and equivalence plus construction. If we have a simply connected space X, we call it rational. If its higher homotopy groups are Q-vector spaces. Or equivalently, we can say that its higher homology groups with integral coefficients are rational vector spaces. And classical rational homotopy theory says that there is a notion of rationalization of a space. If you have a simply connected space, you can always associate, there is always uniquely defined up to homotopy map to a rational space in universal. And you can also say that it is a rational homology equivalence. So yes, you can say that the homotopy category of simply connected rational spaces is reflective inside of homotopy category of all simply connected spaces. Okay. Another thing that I wanted to remind you is the notion of equivalence plus construction. If you have a connected point space X, and you have perfect normal subgroup inside of the fundamental group, the equivalence plus construction of X corresponding to P, I should say, depends on P, of course, is a map which is uniquely defined by the following two properties. It is a map to another space, to a new space, which is uniquely defined by the following two properties. The kernel of the map induced on the fundamental groups is P, and the homotopy fiber of Q is acyclic. Or equivalently, there are actually many other equivalent definitions, but here you can say that the fundamental group of this guy is just quotient by P, and you can also say that this map is homology equivalence in the strong sense. It induces an isomorphism on homology with coefficients in any local system of abelian groups. And this property is equivalent to this second property. Okay, so I reminded you rationalization of a space, equivalence plus construction. So now we are ready to speak about Bousfield-Kan completion. First, I don't want to give you the definition, because the definition is quite technical and tricky. I want to tell you properties, some properties. Bousfield and Kan in 70s introduced such notion, which they called R completion, where R is a commutative ring. It is a functor from spaces to spaces. Yes, a functor from spaces from all spaces to all spaces without any restrictions and without choice of base point. Here I can see this. This is the category of all spaces without base point. And if X is simply connected or nilpotent space, if you know about them, then their rational completion is just ordinary rationalization that I mentioned on some previous slides. And integral completion is just the identity factor. But this one is trivial only for nice spaces, simply connected or nilpotent. If your space is complicated enough, integral completion is not identity factor. It is tricky factor. For example, if your X is connected, but the fundamental group is perfect, non-trivial perfect group, then this is very non-trivial, and this coincides with the equivalence plus construction, where associated with the whole perfect fundamental group P. And actually, this can be generalized to some larger class of spaces. For example, this equivalence plus construction is useful in the definition of equivalence K theory, algebraic K theory. And in this definition, you can replace plus construction everywhere by Z completion. It will be the same. So yes, it is very non-trivial functor even when R is equal to Z. if x is if r is equal to z mod p, then at that point there was already a construction of Sullivan's per P completion, and under some finiteness conditions, this Z mod P completion, Bousfield-Kan Z mod P completions coincides with the Sullivan per P completion. And the main reason why these guys, Bousfield and Kan, were interested in this construction was that they wanted to generalize the unstable Adams spectral sequence to all spaces without any assumptions. And this R completion is equipped with some special spectral sequence, which we can call Adams. Nowadays, it's called Bousfield-Kan spectral sequence, actually, whose first page depends naturally only on homology with coefficients in R, but it converges to the fundamental to the homotopy groups of the completion. For example, if R is Z and X is simply connected, this converges from the integral homology of X to the homotopy groups of X. Okay, now let me give you the definition, but it's quite complicated, so if you don't understand it, it doesn't really matter. For those of you who want to know the precise definition of the Bousfield-Kan completion, I can say that, remember, we considered the monad of free R-affine space, set, R-affine what space is. It was a monad from the category of sets to the category of sets. Here we extend this monad to simplicial sets, just level-wise, and denote by the same letter, RF. This monad, this is a monad, first of all, also a monad, and it sends a simplicial set to a new simplicial set whose homotopy groups are restricted homology groups of the original simplicial set. Here, note that I don't assume that we have a base point, but I still consider restricted homology. What is restricted homology if we don't have a base point? We need to define it only in only zero restricted homology, right? And in this case, where I don't choose a base point, this is just a fine subspace of the ordinary zero homology. It is not abelian group in this case. If we fix some point, we immediately obtain the structure of abelian group. But if we don't choose a point, it is just an affine subspace of the ordinary zero homology group. Okay, we have a monad. This means that we can take the Kabar construction. We know that any monoid and any monad in particular defines a functor from the augmented simplex category. Here we forget about the augmentation and obtain a functor from the ordinary simplex category. To what? Actually, we need to we obtain a functor from delta to the category of n the functors of simplicial sets, but we evaluate this at some simplicial set X and obtain some cosimplicial simplicial set, and then we consider the limit, the homotopy limit of this functor. And if you are familiar with the notion of totalization of cosimplicial object, you can replace this homotopy limit by totalization of cosimplicial objects. In this case, they are the same because this is a redefibrant object. This is the definition of R completion of a simplicial set X. If it looks too complicated, just forget about it. Later, maybe I will give you some better definition. Actually, my talk is devoted to some better definition. Okay, now I can tell you about the main result of our talk. I will try to not assume that you know much about infinity categories, but you just need to know that there is some generalization of the classical category theory, which has some more homotopy theoretical flavor. And in some sense, all classical algebraic topology can be embedded into this theory, is a part of this theory, and all classical category theory can be also embedded into this theory. And many, like all classical categorical constructions, can be generalized to this setting somehow. In particular, adjoint functors, Kan extensions, and so on and so on. Everything can be generalized. In particular, we can generalize the notion of codensity monad. I call it codensity infinity monad because we work in the setting of infinity categories. And for the moment, I will just say that if we have a full subcategory of an infinity category C, then the associated codensity monad is just the right Kan extension of the inclusion along itself. Okay, so we have such an elementary definition. For the moment, I don't want to explain what infinity monad means. It is just a functor which has some universal property with respect to the inclusion of D to C. And now I want to consider one special category and some special subcategory, infinity category. We have the infinity category of spaces, the object that we study in the algebraic topology. And we have, in this category of spaces, we have some nice spaces called Ehrenberg-MacLane spaces, which have only one homotopy group. And we fix some ring and consider Ehrenberg-MacLane spaces of R modules and take all their products. And we also need to, by some technical reasons, we need to include empty set in our K of R. So K of R is the full subcategory generated by the empty set and all products of Ehrenberg-MacLane spaces. Very natural subcategory of the category of all spaces. And our main result with Emmanuel is that this Bousfield-Kan R completion is the codensity infinity monad of this subcategory. So what is the main point? The main point that originally this Bousfield-Kan completion was just defined by some very explicit construction. We could see that it has many nice properties. It is related to many other important constructions, but we didn't have any universal property. And our goal was, in some sense, to define this notion using some universal property. It was very fast we understood that we couldn't do it with, in the setting of ordinary categories, and we have to use this machinery of infinity categories. And then we understood that this is just universal functor which makes this triangle commutative, where this is subcategory consisting of products of Ehrenberg-MacLane spaces of R modules. Oh. No, no. Yes. Huh? Yes. No. What's the point? No. For example, we know that for simply connected spaces and R equal to Z, it is identity factor. No, it is this unstable homotopy theory. Okay, and as a corollary, we obtain some other statements. For example, we obtain that this R infinity is the terminal functor in the category of infinity monads, preserving these products of Ehrenberg-MacLane spaces. So yes, so it has some universal property not just as a functor, but it also has some universal property as an infinity monad. And it is very interesting because there is a long story behind the structure of monad, some kind of monad on this functor of Bousfield-Kan completion. In the original book of Bousfield-Kan, they write that, okay, this functor on the category of simplicial sets has a structure of monad. This is the multiplication map, this is the unit map. But they don't check associativity, and this is not true. It is associative only up to homotopy. And later, the book was written in 1972. Like 30 years later, Bousfield wrote an erratum about it. And okay, sorry, we had some kind of mistake. It is only up to homotopy. And then Bauer and Liebman wrote 2 papers about how to define infinity monad structure in such cases. So it is tricky. It is tricky to define such a structure. But in our case, it is automatical by universal property. Our universal property of this Bousfield-Kan completion implies that there is a uniquely defined, up to not so uniquely as usual, up to some contractible space of choices, structure of infinity monad here. Okay, and now I will tell you some more technical details about it. And now I will assume that you know something about infinity categories. And by infinity category here, I mean infinity 1 category, and I mean the quasi-category. So it is a simplicial set satisfying some additional properties. Okay, and I define, there are, you can find, in the literature, you can find many different definitions of monoidal categories, infinity categories, and some other related structures. We choose the approach which is close to the approach of Friel and Verti, but we reformulate it slightly in our terms, and we say that a strict monoidal infinity category is basically a simplicial monoid whose underlying simplicial set is an infinity category. This is our definition. Or you can say it is infinity category equipped with the structure of simplicial monoid. In general, the category of simplicial monoids, ordinary simplicial monoids, is very important in our study. For example, if E is ordinary strict monoidal category, of course, its nerve will be simplicial monoid, where the product is defined just component-wise in the obvious way, using the tensor product in E. And this will be a strict monoidal infinity category. This is one example. As before, as in the case of strict monoidal categories, here we have 2 important examples. This example, the nerve of ordinary strict monoidal categories, and another example is endomorphisms of endofunctors of infinity categories. If you have an infinity category, you can consider the category of endofunctors, functors from C to C. It is equipped with a natural composition, which gives you a structure of simplicial monoid on this infinity category. So again, you obtain a strict monoidal infinity category structure with respect to this composition. Okay, now I want to define notion of infinity monoid in a strict monoidal infinity category. Let me remind you that on one of the first slides, I told you that for ordinary strict monoidal category E, monoids are in one-to-one correspondence with strict monoidal functors from the augmented simplex category to this strict monoidal category, and we use and we generalize this definition to define an infinity monoid. And by definition, an infinity monoid with strict monoidal infinity category E is a morphism of simplicial monoids. This guy is simplicial monoid. This guy has a natural structure of simplicial monoid because this delta plus is a monoidal category. So both of these guys are simplicial monoids, and we define an infinity monoid as a morphism of these simplicial monoids. Okay, we need not only monoids themselves, infinity monoids themselves, but we also need the category, the infinity category of infinity monoids. And here we work in the category of ordinary simplicial monoids. This is very nice category, and it has standard simplicial model category structure. In particular, it can be naturally enriched over the category of simplicial sets. And we take the mapping space in this category and define the infinity category of infinity monoids in E as this simplicial mapping space in the simplicial category of simplicial monoids. So it is a simplicial set, and it is not difficult to check that it is a quasi-category, that it is an infinity category. Because the forgetful functor from this to E is in the fibration. Okay. And as usual, the definition of infinity monad can be reduced to infinity monoid. Infinity monad is an infinity monoid in the strict monoidal infinity category of functors. Okay, I already told you that it is difficult to define the structure of infinity monad on the Bousfield-Kan completion, but this is a general problem in some sense. Sometimes it is difficult to define structure of infinity monad on a given functor, but it is possible to do this if it satisfies some terminal universal property. Here we consider a general strict monoidal infinity category, and for us, remember that for us it is important. The most important case is the category of end functors, and actually not the category of end functors itself, but all its subcategories close with respect to composition. And we denote by this the category of co-augmented objects, which are just objects of E equipped with the map from the unit object. And of course, we have the forgetful functor from the category of infinity monoids in E to the category of co-augmented functors. And this is a very nice functor. It is not just inner fibration, but it is also isofibration and moreover conservative isofibration, but that it doesn't, and all fibers of these functors are Kan complexes. So you can define such a notion as the space of structures of infinity monads on a given co-augmented object. But the main theorem here is that if you have a terminal object in the category of co-augmented functors, then you can always lift it to a terminal object of infinity monads. This is a complicated theorem that we proved together with Emmanuel, and this is key theorem in some sense to define. Without this theorem, we can't even say that codensity infinity monad is an infinity monad. Yes, so any terminal object can be equipped with the structure of infinity monad, and this is uniquely defined up to contractible space of choices, and it defines terminal object in the category of infinity monoids. Okay, and now I will tell you about some more general version of our theorem, then just version about Bousfield-Kan completion. I already gave you the definition of codensity infinity monad, but you can also say that this is a terminal object in the category of functors from C to C, which are over D, meaning that they give a commutative triangle with two inclusions from D to C. This is actually not equivalent. I don't understand this sophisticated point very well, but this is a property of codensity infinity monad in the setting of infinity categories, but not equivalent. And the same is true in general about Kan extensions. In the classical category theory, there are several equivalent definitions of Kan extensions, but they're not equivalent in the setting of infinity categories. But I don't know counterexamples, I just read it in the book of Lurie. And Okay. Initially, by definition, this codensity infinity monad is just a functor, but using the theorem from the previous slide, using this universal property of this TD, we can equip it with the canonical structure of infinity monad, which is not uniquely defined. This is the problem where the classical language doesn't work very well. This codensity monad this structure of canonical structure of infinity monad is not uniquely defined. It is uniquely defined only up to homotopy in some sense, or you can say up to contractible Kan complex of choice. Okay, but we have it, and this is enough for us. We don't need the unique choice. Okay, and now I want to define you something like Bousfield-Kan completion, but in more general setting and more infinity categorical setting. Assume that we have some infinity monad, which is just morphism of simplicial monoids from this simplicial monoid to this simplicial monoid. And we can forget about this plus here, restricted to the ordinary simplex category, the nerve of the ordinary simplex category, and take the limit. Take the limit in the infinity category of end of functors, if it exists. No, we assume that the category is nice enough, so this limit exists. Actually, this is a limit of a cosimplicial object, and like it is something like homotopy limit of cosimplicial object because we work in the setting of infinity categories. And yes, exactly. It depends on how you think about totalization, but maybe it is better to say that it's homotopy totalization because there are different approaches to the notion of totalization which are not equivalent to each other. Okay, and so that yes. So this limit can be replaced by it is just the same as homotopy totalization of cosimplicial object exactly. The functor, this m hat, no. I have a big comment about idempotency of this is generalization of Bousfield-Kan completion. Bousfield-Kan completion is not idempotent. And maybe the most famous result of my life is that if you take the weight of two circles and take the Bousfield-Kan Q completion, the Bousfield-Kan Q completion is not idempotent on this space. If you apply it twice, it is not the same as once, and this was an important question in algebraic topology. Is it idempotent on finite CW complexes? And no, it's not. We prove that if category C admits limits of cosimplicial objects, or instead of this, you can say if it admits homotopy totalizations, and M is an infinity monad on this category C, then there is an equivalence. This M completion defined by M is equivalent to the category. Is equivalent to the codensity monad of the subcategory, which we denote by A of M, a subcategory, full subcategory consisting of objects that admit the structure of algebra over this monad. I told you nothing about algebras over monads. If I have time, do I still have time? Okay. In the last slide, so from the point of view of my co-author, Emmanuel, this is the main theorem of our paper. This is a more general version because he believes that it can be very useful for some other examples of monads. Anyway, general ideology that all completion-like functors in algebraic topology or not, in some more classical setting, they can be interpreted as some codensity monads, and this is useful. some codensity monads of subcategories, codensity monads of full subcategories. Okay, what is an algebra? Yes, result about Bousfield-Kan completion is a particular case of this general theory. Let me tell you a little bit about algebras over models. And if you have a classical setting and C is ordinary category and M is a monad, then algebra is defined as an object C equipped with some map from M of C to C, satisfying the ordinary associativity and unit axioms expressed in the form of some commutative diagrams. But when we want to generalize it to the case of infinity categories, we need to use the same strategy as we used with monads. We need to find something like walking monoid or walking algebra in some sense, or walking action. I don't have much time, but in some sense, instead of delta plus, we should consider so-called delta max, or sometimes it is denoted a delta infinity. It is a wide subcategory of the simplex category, so the objects are the same, and morphisms are order preserving maps which also preserve the maximal element. And the category delta plus has an action on this category by joint action by this map, and then in some sense this is walking action. So we can define an algebra over an infinity monad M on some category C as an object equipped with the functor from this delta plus to C, which sends zero object zero from this guy to this chosen object C, and such that it respects the structure of action of delta plus on delta max and structure of action of and the functors on C. This is what I wanted to say. Thank you very much.
Thank you very much. Are there any questions?
So for the last part, you defined a M completion for a monad. What if M is not idempotent? Do you still consider the full subcategory of objects having an M algebra structure instead of the category of M algebras?
What if M is not idempotent?
Yes.
M is not necessarily idempotent. M is any. Here, by M, I denote arbitrary monad, not necessarily idempotent.
So maybe it's, I doubt it's morally correct to consider the full subcategory spanned by objects having a structure of M algebra.
Full subcategory of objects having structure of M algebra, yes.
Yes, it's like saying we consider the full subcategory of sets having a group structure, which is the whole category.
Yes, yes. It is not necessarily unique. We don't fix the structure. That's what you mean. Yes.
I see.
Maybe it sounds weird, but here we consider full subcategory. Yes, exactly as you said, as a subcategory of sets having a structure of a group. We don't fix the structure. It just should exist. But actually, here we can replace this A of M by some other categories. Actually, we have some more general result. It should be some category instead of A of M. We can replace it by many other, which may be, from this point of view, more natural subcategories. Okay, let me tell you a little bit more. Okay, yeah, you can say that we replace A of M by the image of this monad. You can just take the image of the functor and that's it. Or maybe more natural will be another category that we denote by S of M. It consists, if we take an object in our category C, and we have this monad as well, we obtain a cosimplicial object that we denote MC, which starts from C, like this is our M0 of C, M0 square of C, and so on, right? This cosimplicial guy. And by S of M, we denote the class the category spanned by objects such that this M of C splits. Such that this cosimplicial object has a natural splitting. Maybe this category looks more natural for you, and this subcategory of this, but this maybe looks more natural, and codensity monads will be the same, because if you close this with respect to retracts, if you add all retracts to this category and all retracts to this category, they will be the same. And actually, this codensity monad depends only on the retract closure of the subcategory.
Thank you.
Any more questions? If there are no more questions, let's send Professor Ivanov again.